Hello everyone, here is your bell work for the day. Go ahead and pause your screen so we can go ahead and get started in the lecture. Hopefully you guys watched the lecture so far. So in this example, we're going to be finding the domain of a function as a set of ordered pairs. So here are all of our ordered pairs, and to find the domain, we simply need to know the input values because the input values are the domain. It's the first set of the coordinates, or the x values, in the ordered pairs. So 2, 3, 4, 5, and 6 are our domains, and to write them, we use this type of bracket to write the domain. All right, now when we get a little bit more complicated and you have a function to find the domain, we're going to go through how to find that. The input value shown by the variable x in the equation is squared, and the result is lowered by 1. Any real number may be squared and then lowered by 1, so there are no restrictions on the domain of this function. The domain is the set of real numbers. In the interval form, the domain of the function is negative infinity to infinity. And if you wanted to try to work this problem out, you could start with a negative number and plug 0 in, and plug a negative number in and plug 1 in to solve for this solution. Another way you could do this is by graphing the function, which we will learn shortly, to discover what are the restrictions of this function. When there's a denominator, we also want to include only values of the input that do not force the denominator to be 0. So we will set the denominator equal to 0 and solve for x. Therefore, we know that 2 cannot equal x because that will make the function equal to 0. So then we know that the domain has to be every number besides 2, all real numbers that are less than 2 or greater than 2. In interval notation, we write the solution as negative infinity to 2 because it goes all the way from negative infinity all the way to positive 2, or you can write this symbol as union to say and, 2 to infinity. So it's pretty much every real number except 2. To show that on a number line, you put a dot with a hole in the middle, or a circle, on the number 2, and you would know that then it's every real number except for 2. If you have an even root, first you're going to have to set the radicand greater than and equal to 0 to solve for x, because you cannot have a square root of a negative number because we do not use imaginary numbers in pre-calculus. After you set the radicand equal to greater than or equal to 0, you want to solve for x because we know that square roots cannot be imaginary numbers and we need it to be greater than 0. So when you solve that, you get x is less than or equal to 7. Therefore, you can exclude any number greater than 7 from the domain. Now you can exclude any number that is greater than 7 from the domain because x less than or equal to 7 will make the number imaginary or not real numbers. The answers are all real numbers less than or equal to 7 or negative infinity to 7. And the tight bracket shown on here tells us that 7 is included within this number. For the notation to show that a function's domain is h is greater than 5 and less than or equal to 10, since it's greater than 5, you don't want to put 5 as included, so you put a circle around 5, and since 10 is included, since it is less than or equal to, you close the hole, so you put a dot on 10. Please make sure to review these, how to notate specific functions on a number line for their domains. Describe the interval shown in figure 6 using inequality notation. Set builder notation and interval notation. Well, we know it's greater than and equal to 1 because 1 is a solid dot. and it's less than or equal to 3 because 3 also has a solid dot. Since the number line is broken, we would need to form a union, so we would also add the union symbol. For 5, the dot on 5 is open, so we know that 5 is not included in this number, so it's greater than 5. So our domain would be 1 to 3 and greater than 5. We would show this with a union. Since 1 and 3 are both included on equal to, we would want to show bracketed parentheses to show that those are the only 3 numbers on the left side of the number line that are included. Since 5 has simply a greater than and it is going to infinity, you can write that as just parentheses instead of brackets. Another way to find the domain, like I stated earlier, is by using graphs. Because the domain refers to the set of possible input values or values of x, the domain graph consists of all of the input values shown on the x-axis in this graph. The range is the possible set of output values which are shown on the y-axis. Keep in mind that if the graph continues beyond the portion of the graph we can see, the domain and range may be greater than visible values. So since the x-axis continues down, but the domain has a certain, but the negative value of x has a certain stopping point on it, then we know that -5 is the lowest number of the domain. The range also starts at +5. So we know that for y values, which is our output value or our range, can be less than 5 because the graph continues to go down the y-axis without an end. For the x values, we aren't sure where they stop, but it does seem that we know where it starts. So it would be -infinity to 5 would be the range because it starts at +5 and goes to infinity. For our domain is -5 to infinity. Because we can't see the end of the graph, you have to assume that it keeps going until infinity. Looking at graphs is a lot easier to see the domain and range. If you're ever confused, you can always put an input value in for the domain and the range to try to help you discover what the actual value is. Your exit ticket will consist of determining the domain and range of certain functions. Go ahead and pause your screens to complete your exit ticket for today. Have a great rest of your weekend.